year 13, because both classes are at slightly different places here in Newton's laws, both of you are missing something. So 13D, you haven't got the little bit of extra notes that we need to do on lift questions, and 13C, you haven't got Newton's third law done yet. So I'm just going to start from the start to make sure that everybody has everything covered. Okay, now the way I am sitting here is very shadowy. I've got a window to my right, so apologies about all the shadows. Hopefully it is still legible, apart from my handwriting. So, Newton's first law, both classes we have gone over this, albeit very, very quickly. But basically with Newton's first law, this is it, the way it is written in Say's textbook. They actually don't tend to ask you to state that one that much in exams, but they still might, so you do obviously need to learn it. But basically what Newton's first law means is that if the forces are balanced in something, so if the forces acting to the right are equal to the forces acting to the left, then that means that the thing's just going to keep doing whatever it's doing. So if it's sitting still, it'll keep sitting still. If it's moving at 10 meters per second, it'll keep moving at 10 meters per second in that direction until the forces are no longer balanced. So they will use that as a sneaky way to like give you the friction forces in a question. Now I am pretty sure everyone has this all filled in. I suppose if anyone was off, you probably don't. But that is what you need to fill in there. So what does this mean? If the forces acting on an object are balanced, it will keep doing whatever it's doing. If there's a resultant force, then it's going to accelerate. So how you're actually most likely to come across that in an exam, how you're going to use it in calculations. If they tell you something is at rest, or if it's going at a constant speed, then that means you can use the fact that the forces are balanced. So say for example something's on a slope and it tells you it's going down the slope at a constant speed, then you know the forces acting up the slope must be equal to the forces acting down the slope and stuff like that. Okay, so forces up equal down, left equals right, whatever angle you're at, they go to the same angle, opposite direction. Now I can't remember if I did this bit with both classes, but this was just me talking through, and this is maybe more a GCSE kind of question, but if you're expected to know it at GCSE, you're obviously expected to know it now as well. So what they might do is tell you, and for some reason the questions often seem to be boats. So whenever a boat has a, say it's going to the right, this boat here, my expertly drawn boat, if it's moving to the right, they might tell you, right, well, whenever there is a thrust or a forward force of 50 newtons, this boat is travelling at a constant speed. And then they'll maybe say, calculate the acceleration whenever the thrust is increased to 80 newtons. Okay, so whenever the forward force was 50, the question maybe had told you it was going at a constant speed. That's their sneaky way of telling you that the friction forces or the drag forces must be 50. So then whenever the forward force increases to 80, then you know the friction forces are 50. So you can use this to calculate the resultant force and then use that in Newton's second law to calculate the acceleration. Okay, so let's have a wee look at Newton's second law. Okay, so this one here, they absolutely ask you to state regularly. Okay, so make sure you learn this one off. And sometimes there's 2 marks for it and sometimes there's 3 marks for it. So just make sure you say it in full every single time to make sure that you're getting the marks for whatever they are being fussy about in your particular year. Now, if you were to stop me and ask me what's Newton's second law, I would say F equals ma. But that's not going to get me marks in the exam. I need to be able to say it in words, and I will then sort of in my head think through F equals ma and what that actually means in words. So if you remember that this whole thing is about relating the acceleration to the 2 other things in the equation, right? So if you have an object and you are applying a constant force to it, if the mass increases, so I don't know how this would even work, but if I am applying a constant force to this pen and the mass of that pen suddenly increases, then the acceleration is going to decrease because it's heavier, it's harder to move it. So that tells us that the acceleration is inversely proportional to the mass. Now, without even thinking it through logically, you can tell that from the equation, because if this equation is true, with a constant force, if you increase this number, the mass, the acceleration has to decrease if you're multiplying the two of those together to give you f. Now the other thing with acceleration then is that it's directly proportional to the force, and that one's probably easier to remember because it's a little bit easier to think through. If I apply a bigger force to something, then it's going to accelerate more. Okay, so this is the way we would word it, and I'll tell you, I'll underline actually what the 3 marks would be for if they decide to award 3 marks for this question. So the acceleration of an object, so acceleration inversely proportional to mass, directly proportional to the resultant force, and the third one is that it takes place in the same direction as the unbalanced force, or we can stick this end resultant there. I don't really know why I've changed that into both, like one of them says resultant and one says unbalanced. Use those interchangeably, they both mean the same thing. Okay, so that's what the 3 marks are for. So we've got the purpley colour there. Acceleration inversely proportional to mass would be 1 mark. Directly proportional to the resultant force is the 2nd mark, and takes place in the same direction as the resultant or unbalanced mark would be, or unbalanced force, sorry, would be the 3rd mark. So what does this mean? All I've done here, and again, the majority of you already have this filled out, but all I've done here is taken this statement, the official Newton's second law wording, and put it into what it actually means. So if you have an unbalanced or resultant force, it's going to cause an object to accelerate. The direction of the resultant force is the same as the acceleration. This here is super important for the lift questions and the little extra notes on lifts. So 13C, you do have the lift notes, but 13D, I didn't get doing that with you. So make sure you have another page ready to write some extra notes down here in just a second. But anyway, the resultant force direction is the same as the acceleration. That can catch some people out sometimes, which I know it sounds obvious at the minute. Oh yeah, well, of course it is, but especially in lift questions, whenever it's moving up or down or accelerating or decelerating, it's so easy to get it the wrong way around. So listen to my advice on lifts. Acceleration inversely proportional to mass and directly proportional to resultant force. Now, how are you going to use this in questions? The most frequent way you're going to end up using this is just using F equals ma. Make sure you remember that the F in F equals ma is the resultant force. It is not just the forward force or just the thrust in the question. And then this was just a wee example that I gave to 13C, I think it was. So 13D, you probably don't actually have this written down. Add it in now if you don't. So this was just a wee made up example we did in class with some mass of 5 kilograms, and it's accelerating to the right. If there's 2 arrows here, it really means it's an acceleration. So say there was a force acting up the way at 10 newtons at 15 degrees to the horizontal, and then this would be like the friction forces if this was getting dragged along the ground. So you would use F equals ma. The resultant force is going to be in the same direction as the acceleration, so the resultant force is going to be the horizontal component of this minus this 3 newtons. So the horizontal component of this 10 Newton force is going to be 10 cos 15. So that's where that has come from. So 10 cos 15 minus 3, that gives me the resultant force equals the mass, which is 5, multiplied by acceleration. And then that's just working through the rest of that equation. Okay. The example on that is in your notes is a person stands on a skateboard at the top of a rough sloping track. The mass of the rider in the skateboard is 73. So this is my skateboarder here with a mass of 73 kilograms. The track slopes at an angle of 9.5 to the horizontal. The rider and skateboard start from rest and move down the track with uniform acceleration of 0.46. So this is my acceleration, 0.46 meters per second squared. During the motion, the force of friction is constant and air resistance is negligible. In the majority of our questions, air resistance is negligible. So part A, calculate the magnitude of the resultant force causing the skateboard and rider to accelerate down the slope. Well, we have the mass and we have the acceleration, so we can go straight into F equals ma. So don't overthink it. My instinct with something like that would be to go into resolving all the forces and everything. We do have to do that eventually, but we've got the mass and the acceleration, so we can find the resultant force. That's all it's asking for, and that's what the F is in F equals ma. So that's all I've done here. F equals ma, the mass 73 and the acceleration 0.46 gets me 33.58 newtons. Now for part B. Calculate the constant frictional force acting on the skateboard as it moves down the slope. So I forgot to actually go through this diagram. We've got the mass, this is their weight, 73 times gravity, newtons. And remember in physics 9.81 for gravity. Friction is going to be acting up the slope because it's accelerating down, so friction always acts opposing the motion. Now in the wee pen here, all I've done is mark on the components of the weight acting perpendicular and parallel to the slope. So remember, whatever this wee angle is here, this 9.5, this is going to be the same angle here, because you've got your wee triangle there, look. This is 90. This is the angle, this is going to be 90 minus that angle. This also makes a right angle, so that ends up being the same as that. So if we needed, we don't for this question, but if we needed the component of the weight that was acting perpendicular to the slope, then it's just going to be 73 times 9.81 cos 9.5. The one that we do need for this is the component of the weight that's acting down the slope. So in this case, it's 73 times 9.81, so the weight sine of the angle, because we're not going to cross it, so it's sine. So in part A we had worked out that the resultant force was 33.58, so 33.58 must be the component of this weight that's acting down the slope minus friction, because the resultant force has to be acting down the slope because it's accelerating down the slope, so it's going to be the force going down the slope minus the force going up the slope. So that's where these numbers have come from. So 33.58 equals the weight, 73 times 9.81, sine of the angle minus the friction. And then the rest again is just me working through the maths of solving that to get 84.6. Right, now 13D, I need you to get a spare page out somewhere. I can't find my spare pages. Oh, here they are here. And we're going to add in a couple of little notes on lifts before we move on to Newton's third law. So 13C, you did get this written down in class, but it'll do no harm to sit and listen to this terribly exciting video. Right, so lift questions. Stick this on your page, please. So whenever I first started, I suppose, teaching this stuff, I always sort of panicked a little bit about questions involving people standing in lifts. There was a couple of things I didn't really realise. So randomly in physics, they tend to ask you questions about, oh, such and such is standing in a lift on a set of scales, and then they're asking you to talk about what the scales show, as if anyone is ever in that situation. But anyway, so let's make a wee note here. If you're standing in a lift, if you're standing on scales in a lift, the scales show the normal reaction. So do you know how, like, if you're standing on the ground or sitting on your seat, you've got the normal reaction force acting up the way? That is really what your scales are showing you. That's what scales show you in real life as well. It's just that is normally exactly equal to your weight. Okay. Now, here's my lift, and here's my person standing or hovering in it. Don't know why I always accidentally draw them hovering, but anyway. Now, In this, we're only really going to be marking on the forces that are acting on the person. So I don't really care about the force of the person pushing down on the lift or any of that. We're only caring about the forces acting on the person. So the person is going to have their weight acting down the way, and then they're going to have their normal reaction force acting up the way. So let's say, we're going to go through all the different options here, but let's say this lift is accelerating up the way first of all. Okay. If it's accelerating up the way, because of Newton's second law, the acceleration is directly proportional to the resultant force and in the same direction as the resultant force. That means the resultant force has to be acting up the way. So whenever we are doing F equals ma, because it's accelerating up, the resultant force has to be acting up the way. So it will be the normal reaction minus the weight. So hopefully that makes sense, because this is the only bit that really changes the whole way through here. Equals the mass times acceleration. Now generally with these questions, the question will be to figure out what the scales show. And remember, the scales show you your normal reaction force. So the normal reaction is going to be equal, in this case, to the weight plus mass times acceleration. Now, normally in class, and I did do this with 13C, but normally in class I get you to imagine, so do still imagine it, you just don't get to see me acting it out this time. But imagine you're standing in a lift, right, and it starts to accelerate up the way, and think about how you feel. So you sort of feel a bit heavy, you feel heavier than normal, and this here explains why. Because if you think about that, the normal reaction is what is showing on the scales, you're ending up increasing your weight here, like the scales show a bigger force. Because, now I didn't write this next line in, you don't need to. This is going to rearrange to give you the normal reaction is equal to weight plus mass times acceleration. Now the reason that I don't normally write this bit here in is because I don't want you trying to learn, right, if it's accelerating up, this is what you get. If it's accelerating down, this is what you get. If blah, 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 blah. Because that's just horrendous to try and learn. I would rather you learned this process here and figuring it out, because that's going to work every single time, no matter what the specific situation is. Yeah, don't try and learn this off by heart. But that's why you have that feeling of, you sort of feel a bit heavier, because your normal reaction is your weight plus mass times acceleration if the lift is accelerating up. So we're going to stick with this lift going up the way. So it's accelerating up, then for a little while in its journey, it's going to go at a constant speed. So you will notice this diagram is exactly the same the whole way through. Because for the person in the lift, they always have their weight acting down the way and their normal reaction acting up the way. Because it's a constant speed, that means Newton's first law applies, so the normal reaction is equal to the weight. So the scales will just show your normal weight at that situation. Oh, one thing I meant to say anywhere in this is that I still never ever will attempt a lift question without doing a wee sketch beforehand. So every single time, no matter how monotonous it is, I will do my little sketch of my person standing in the lift with their weight down, their normal reaction up. I'll mark on the acceleration and then I'll go over and do this. Right? Anyway, so your lift has started to accelerate up the way, it's gone at its constant speed, and then whenever it reaches the floor you're going to, it decelerates, but it's still moving up. So let's word that differently than I did with my other one. Moving upwards, but decelerating. Okay. I wasn't lying. I do my little diagram every single time. There's my person. We've got their weight acting down. We have their normal reaction acting up the way. So this thing is moving up the way, but it's decelerating. So that means its acceleration is going down the way. And with ones like that, I do one arrow to show the direction and then the double arrow to show the direction of the acceleration. Keeps it right in my head. Now, before we go through this, have a wee think. If you're standing in a lift and it's moving up the way and you are starting to decelerate because you're reaching the floor, how do you feel then? You feel kind of light, like ever so slightly floaty. And this equation will show you why. So because there is an acceleration, then we use F equals ma, obviously. Now this time, because the acceleration is acting down the way, the resultant force has to be acting down the way. So our resultant force here is going to be weight minus normal reaction equals mass times acceleration. So again, if we rearrange this to make the normal reaction be the subject, we are going to end up with this. So the normal reaction is weight minus mass times acceleration. So I keep talking about how, oh yeah, the normal reaction is what the scales show. It's really, that's what you're feeling as well. You're feeling the reaction with the floor. So whenever you are in the lift that's moving up the way but it's slowing down and you feel light, it's because the normal reaction is what you feel. So you've got your weight minus acceleration this time, so that's why you have that sort of light feeling. Okay, we're going to do lifts moving down the way as well. So this time we will go accelerating down. So you've gone upstairs in the lift and now you're going back downstairs again. Or not downstairs, we're going to say you're in a lift. You're going back down in the lift. So here you are in your lift. You've got your weight acting down the way, your normal reaction up the way, and it's accelerating down. Again, have a think for me. How does that feel? Do you feel heavy or light? In this situation, you're going to have that light feeling. So we can see where we're going to end up with this. Because our acceleration is down the way, our resultant force is down the way. So the resultant force is going to be the downwards force minus the upwards force. And again, that rearranges to give us that one. Remember, don't bother trying to learn off that. There's no point. You'll mess it up. You'll do it wrong, mess up. Whereas if you just think it through, it's easy. Then the lift is going to go at a constant speed for a little while. So constant speed means Newton's first law. So at this stage in the lift, your normal reaction is just equal to your weight. So that you feel your normal weight at that stage, and the scales will show your normal weight. Then, whenever you, oh, I forgot to reword this. Whenever you are going down and you reach the floor you're getting to, the lift will start to decelerate, and it is moving downwards this time still. Now, I know where I'm literally drawing the exact same diagram every time, but I'm not lying. I do it every time I do one of these questions. So this time, lift is going down and it's decelerating going downwards, so the acceleration is going up the way. So again, F equals ma. Oh, here, before I do it, have a think. You're in a lift, the lift is moving down, and it's slowing down because it's reaching the floor that you're getting to. How do you feel? Feel heavier, and that is because your normal reaction ends up being bigger than your weight. So because the acceleration is up the way here, our resultant force must be acting up the way. So the resultant force is the normal reaction minus weight equals mass times acceleration. So if we were to rearrange that, the normal reaction, which is how you feel, is equal to weight plus mass times acceleration. Okay. This is a big page to have in your notes because it really helps me do these questions. So that means it'll really help you as well. Okay, right. Anyway, back to the original notes. Where am I? Newton's third law. So some people do have Newton's third law already filled in, but listen anyway. Sure, what else are you doing? So Newton's third law is the one that everyone seems to remember, that every action force has an equal but opposite reaction force. But it's quite often misunderstood. So this is it worded the way it is in Say's textbook. If body A exerts a force on body B, then body B exerts a force of the same size on body A, but in the opposite direction. Now, the way that it is quite often misunderstood is this here. So forces come in pairs. One's the action, one's the reaction. So how come the forces don't cancel each other out? So quite often people are like, well, how do we ever get a resultant force if there's equal but opposite forces? And the reason is that anytime we are drawing a free body diagram, so like for example these lift questions that we were just doing here, we're only ever drawing the forces that are acting on one object. That's what free body diagram means. So here I'm only ever drawing the forces acting on the person. I'm not drawing the equal but opposite forces to these because they're acting on different things. So for example, with this person that was standing in the lift, the equal but opposite force of their weight is the gravitational pull of the person on the earth. So there's an equal but opposite one on the earth here. And the equal but opposite one from the normal reaction is the contact force between the person and the lift. So because the equal but opposite forces of these aren't acting on the same thing, on the thing that we're drawing the forces for, we don't include them. Yeah, so this one I kind of wish we were in class to explain because this is the one that causes the most problems. Anyway, so how come the forces don't cancel each other out? Let's get our notes written in and I'll blather away as I'm doing it. So the forces of an action-reaction pair, and you'll hear me switching between calling it an action-reaction pair and a Newton's third law pair. So either or. I think I prefer Newton's third law pair. Always act on different bodies. So that's how we end up with a resultant force acting on one body, because the equal but opposite one is acting on something else, so it's not taken into account with the original body we're talking about. So this means they do not combine to give a resultant force, and cannot cancel each other out. Now, if you have two forces that are acting on the same body, then they're not an action-reaction pair, even if they might be equal in size and opposite in direction. So, like in this situation here with the lift that was going at a constant speed, yes, these two are equal in size and opposite in direction, but they're not a Newton's third law pair. Newton's third law pairs always act on different objects and they're always the same type of force. So weight is a gravitational force and your normal reaction force is a contact force. So they're breaking all the rules, they're acting on the same object or person, so that means they're not a Newton's third law pair, and they're not the same type of force, so they're not an action-reaction pair because they're not the same force. It's just that they happen to have the same size, which is where all the confusion comes from. So, two forces that act on the same body are not an action-reaction pair. Even though they may be equal in magnitude and opposite. Oh, I've spelled that wrong. Embarrassing. Hold on. Oops. Yeah. I'm a nightmare. There we go. And opposite in direction. So, sneak in a wee extra note in 13B. I don't think you do have this written in. They must be, so to be Newton's third law pair, forces must be of the same type. So magnetic force, gravitational force, a contact force, electrostatic force. Okay. And act on different bodies. Now, my little sneaky way to figure out what the Newton's third law pair on something is to literally change the order of the words that you're saying it. So hopefully that'll mean, or that'll make a little bit of sense whenever we go through this example here. Okay, so with the case of something resting on a table, so if we have an apple resting on a table, there's actually 4 forces acting here, but we only ever draw 2 of them, because do you remember what I was saying? We only ever really draw the forces acting on one thing. So in this situation, we would be marking on the forces that are acting on the apple generally. Okay, now the 2 forces acting on an apple sitting on the table, so the weight acting down the way and the normal reaction acting up the way, do happen to be equal in size and opposite in direction, but they are not a Newton's third law pair. So there's 4 forces acting on total. There's 2 acting on the apple, so they're not a Newton's third law pair, but each of those 2 have a Newton's third law pair. So we're gonna draw the 2. We're going to end up drawing a bunch of diagrams here, but we're going to draw the 2 third law pairs acting separately, and then we'll do free body diagrams for the apple. We'll just do it for the apple. Okay, so the first one, let's think about the weight of the apple. So if this is my apple, right, and it has its weight acting down the way, I'm going to label that a little bit differently. So this is the gravitational force of the earth on the apple, right? That's the weight, the force of the earth on the apple, the gravitational force. So the equal but opposite version of that, and do you remember what I was saying about your sneaky wee way that you can like figure out what it is? This is my earth, by the way. The whatchamacallit, equal but opposite is that of that. You just change the direction of the words. So we've got the gravitational force of the earth on the apple. The equal but opposite of that is the gravitational force of the apple on the earth. So same type of force, and just change the order of the way you say the words, and it works out. So let me go on a little bit here about what on earth this is, the gravitational force of the apple on the earth. So technically, absolutely everything that has a mass has a gravitational field around it. So the apple has a tiny gravitational field around it, and therefore will attract anything else that has a mass. So you sitting, trying to stay awake, listening to this, have a gravitational field around you, and then the pen that you're holding also has a gravitational field around it. Absolutely everything does. It's just that it is so tiny in comparison to the gravitational field of the earth, because the earth's mass is so big. So the bigger the mass of something, the bigger the gravitational field around it. So if you have a wee, like, look up, I think I showed one of you this, I definitely showed it at GCSE, but have a wee look on YouTube. There's a clip of a Family Guy episode where there's a joke about this, where Peter gets so fat that his gravitational field increases so much that things start to orbit around him. So I love it whenever there's little physics jokes and things like that. Keeps me happy. Anyway, we've got notes to write with this. So, this is the apple, this is the earth. So the earth pulls the apple down. With a force, and we've called that F, force of the earth on the apple, FEA, earth on apple. This is a gravitational force, which we call the weight of the apple. So this is the action force in our action-reaction pair. So the equal but opposite of that is the gravitational force of the apple on the earth. So that means the apple attracts the earth with a force FAE, the gravitational force of the apple on the earth, which is equal in magnitude but opposite in direction. So that's the reaction force. So right now you are being attracted to the earth because of the earth's gravitational field, but you are also attracting the earth because of your gravitational field. Hopefully that makes some sense, because whenever I'm teaching this stuff here, the Newton's third law pair stuff and the lifts actually are where I get the most questions. So please make sure you do ask me questions on anything that you're not sure on, especially whenever you're doing questions. Right, anyway, over the page we are going to start to think about the other forces that are acting. So remember, this whole situation we're talking about here is an apple sitting on a table. So, or sitting on the earth, I suppose I should say. Should we pretend it's sitting on the ground? No, we'll stick to it on the table. So here's my apple on the table. So the force that we normally just mark on here is the normal reaction force. So that is the force of the table on the apple. But equal but opposite to that, the apple is also pushing down on the table. So the force of the apple on the table. This, it is so important to note, is not the weight. It is equal in size to the weight and in the same direction as the weight, but it is not the weight because this is a contact force. Right? So, I'm going to be doing this in the opposite way. So the apple exerts a force, F-A-T, force of apple on table. So apple on table, and that is a contact force. That is the action force. So the table pushes back on the apple. So the table exerts an equal but opposite force, FTA, force of table on apple. Table on apple. And again, that's a contact force. And that's the reaction force. So, yeah, there are different types of forces than the weight, but they're all four of these forces, by the way, are the exact same size. Normally though, whenever we're doing questions, we only care about 2 of them because we only care about the ones that are acting on the apple. So if I was to draw a free body diagram for the apple, oh, there's me spelling things wrong again. So free body diagram of the apple. Right, here's my apple. The first one, if we go back here, we had the gravitational force of the earth on the apple, which was its weight, acting down the way. So the force of the earth on the apple, now we call that its weight. And then we had from up here the force of the table on the apple, and we call that the normal reaction force. Oops, sorry. So whenever we draw our free body diagrams, we only draw the forces acting on the one thing. So these 2 things, yes, they are the same size as each other. Yes, they're in opposite directions, but they are not a Newton's third law pair. They're not an action-reaction pair because they're acting on the same object for one, and they're they're acting on the same object is the first reason, and the other reason is that there are different types of forces. This one is a gravitational force and this one is a contact force. Right, I think I have rambled on enough, and if you're still listening to me, congratulations. So I will make a wee list of the questions I want you to do. I will probably might end up doing these ones. I was going to say I'll probably leave these out and just go straight on to the exam ones. Probably do the exam ones first and then maybe go back to those, because the exam ones are better prep to do anyway. Right, anyway, gotta go. Have fun. Sorry for rambling on for 38 minutes. Oh my word. Okay, bye.